Hi everyone, this is the video on isomers for AS level chemistry. So for AS, there are two main types that you need to know. There is structural isomerism and stereoisomerism. Under structural, there are three different types: positional, functional, and chain. And under stereoisomerism, there are also two different types. There are cis-trans or geometrical isomers and optical isomers. So starting with structural isomerism, a structural isomers are isomers that have the same molecular formula, but they have a different structural formula. So you can arrange them differently to give different compounds. Let's start by talking about positional isomers. In positional isomers, the location of the functional group varies in the molecule. So if we look at this example of C3H6Br2, there are a number of different ways you could draw this to give different positional isomers. One way in which you could draw this is to put the bromines on the first and second carbons, and this would give you 1,2-dibromopropane. Alternatively, you could draw it with the bromine being on the first carbon and on the third carbon, and this would give 1,3-dibromopropane. You could also put both of the bromines on the same carbon, so let's say we put both of them on the first carbon. In this case, you would have 1,1-dibromopropane. And another way you could do this is to put, again, both the bromines on the same carbon, except we'll put them on the second carbon instead to give a different compound, and this would be 2,2-dibromopropane. So, although the molecular formula is the same, the molecules are actually different because the bromines are all in different places. And the important thing to remember here is that there is free rotation around this carbon-carbon double bond. So it's possible that you might accidentally make one drawing that can simply be rotated to make another, in which case it wouldn't be an isomer, just a different way of drawing it. Let me show you an example of this common misconception. So if we looked at this first molecule over here, with the bromine on the first carbon and on the second carbon, another way you could actually draw this would be to put this bromine over here. Now, although they look different when you initially look at them, they're actually the same because the carbons are still the same. So if I was to label the carbons, this would be the number. You'll see that the bromine here is on carbon 1, this bromine is on carbon 2, and same thing here. The bromine is on carbon 1, and this bromine is on carbon 2. So they're essentially the same molecule. You have to be careful in exams or when you're practicing that the same structure is not repeated. Remember, in order to create a positional isomer, bonds have to be broken. If you simply twist the molecule to make another, it is not an isomer. When two molecules have the same molecular formula, but they have different functional groups present in them, this is called functional group isomerism. And since the isomers have different functional groups, they also have very different chemical properties. So an example of this would be looking at C3H6O. Now there are two ways that I could draw this. One would be as an aldehyde, and the other would be as a ketone. So let me draw both and show you what they would look like. So as an aldehyde, you would have 3 carbons in the main chain, and you'd have a double bonded oxygen and a hydrogen on the other. So if I draw the rest of the hydrogens in for this would be called propanal. Whereas the ketone, again, there are 3 carbons in the main chain, but a ketone is double bonded to just the oxygen with no other hydrogens present. So this is what this molecule would look like. And this is called propanone. Now you can see that they both have the same molecular formula, which is C3H6O, and you can count the hydrogens to see that they have the same number of hydrogens, same number of carbons, and same number of oxygens. But the functional groups here are very different. This is a carbon bonded to a hydrogen and a double bonded oxygen, whereas this is just a carbon bonded to a double bonded oxygen and two other carbons. And remember that having these two different functional groups gives them different chemical properties. The third type of structural isomerism that we need to know about is chain isomerism, and this is where the carbon skeleton itself is different for the molecules. So, for example, let's look at this molecule, C4H10. Now, at first glance, it looks like butane, and it could be butane, but what it could also be is methylpropane. So, the two different ways that these could be drawn is it's all based on the carbon skeleton. So for butane, you would have the 4 carbons in a straight line like so, whereas for methylpropane, you would have 3 carbons in the main chain as suggested here by the propane, and you'd have a methyl group. Now, the important thing to remember is where to put the methyl group. If it was here, this would not be methylpropane. This would just be butane because this carbon chain is continuous. When there is a methyl group, and you have to ensure that it is not part of this straight chain. So in this case, the methyl group would come up here. If I was to draw it in skeletal formula to make it a bit clearer, it would look like this. This is butane, whereas this is methylpropane. So you can see here that the carbons go from 1, 2, 3, 4, whereas here there are only 1, 2, 3 in the main chain, and the fourth one is actually a methyl branch. So now moving on to the other main type of isomerism we need to know, which is stereoisomerism. So stereoisomers are molecules that have atoms bonded to each other in the same way, but they have a different arrangement of atoms in space. So the molecules do not superimpose on each other. Starting with geometric isomerism, the molecules are either unsaturated or are ring compounds with the same molecular formula and order of atoms, but different shapes. So the first thing to note is that there is a carbon-carbon double bond present. So unlike carbon-carbon single bonds, there's no free rotation around this carbon-carbon double bond, and this is due to the presence of a pi bond in this double bond. So in order for geometric isomerism to occur, there must be two different groups on the right side, and there must be two different groups on the left side. And the molecule must be unsaturated, which is the carbon-carbon double bond. So if I give you an example of what I meant by two different groups on the right and two different groups on the left, so for there to be two different groups on the left, let's say this is group X and this is group Y, and this is group X and this is group Y. This molecule would show cis-trans isomerism because X and Y are different groups and on the left, and here X and Y are also different groups on the right. What would not be an example of cis-trans isomerism is if the groups were the same on the left and if they were same on the right. So for example, if you put two X's on the left and you put two Y's on the right, this would not show cis-trans isomerism because here X and X are the same, and on the left and on the right, Y and Y are the same. So this does not show geometric isomerism. A cis isomer has atoms that are on the same side with the double bond. So let's say I use the X and Y example again. In this case, this would be X, and this would also be X, whereas this would be Y, and this would also be Y. So what I mean here is that the X groups are the same on top, and the Y groups are the same on the bottom, but also, importantly, the X and Y groups are different on the right, and the X and Y groups are different on the left. So for a cis isomer, top and bottom are the same, whereas left and right are different. Now remember that this bottom rule applies to all cis-trans isomers. but I'm just writing it down to clarify what I mean. Then when we look at trans isomers, a trans isomer has atoms that are on opposite sides of the double bond. So if I drew another molecule, so let's use the X and Y example again. This would be a trans molecule because here the top groups are different, so X and Y, and the bottom groups are also different, Y and X. But also importantly, to fulfill the main requirements, the groups on the left are different, X and Y, and the groups on the right are also different, Y and X. So for trans isomerism, the top and the bottom are essentially kind of the same, but they're in a different order, so technically they are different. And what I mean here is that if you read this from left to right, you'd see that X comes first and then Y, whereas on the bottom, Y comes first and then X. And again, left and right must be different. One way I like to think of it is for trans isomerism, I like to think of it like a diagonal. So for example, let me just redraw that molecule I drew in earlier. I like to think of it as they're diagonal to each other. So the similar groups, which in this case are here Y and here Y, they are diagonal to each other this way, whereas the two X groups are diagonal to each other this way, compared to the cis isomer, where they are both parallel, like this. That's how I like to think of it. Cis is they are parallel, and trans, they are crossed over like that. Here are some examples of cis-trans isomerism. So let's look at the first one on the left. Here we can see that the hydrogens are the same on top, so there's an arrow going this way, and the chlorines are the same on the bottom. Now since these arrows are parallel, like I showed you my hack earlier, this would be a cis isomer, whereas here the hydrogen here is on the left and this hydrogen here is on the right, so they are diagonal to each other, and the chlorines here are also diagonal, so this would be a trans isomer. Also remember that for the trans, it should be different when you read it from left to right. So here, if you read it from left to right, you would see that first you get a hydrogen and then a chlorine, whereas on the top, whereas on the bottom you get a chlorine and then a hydrogen, which makes it trans. Here's another example, except this time I'm using skeletal formula. So this is what 3-methyl pentuene looks like. Now if you try to draw this as firstly a cis isomer, then the trick to this is to draw the double bond as a straight line first, so you can see where the rest of the groups are going. Now from here, if I look at this group comes down here. Now let's look at this group. This one comes down here. And lastly, we have this, which comes up here. So that's how you would draw the cis isomer. And you can see that it's cis because this group and this group are the same, whereas this group, which would just be a hydrogen essentially, and this group are different. Now, I know that in the previous example, obviously, we looked at these two being identical. We looked at these two being identical to each other. Now, this is not always the case. The top and bottom groups can actually be different to each other as long as one of them satisfies the requirement of being the same, in which case the methyl group here and the methyl group here satisfy that requirement. That means the top one doesn't have to be the same as long as the bottom one is the same. The opposite argument also works, so as long as the top is the same, the bottom does not have to be the same. Let's look at the trans isomer for this. So again, draw in the double bond first to make it easier. Now for the trans one, we'll actually shift this methyl group over here up instead. And we'll keep this one down there. And we'll keep this group up here as before. Now you can see that the methyls are actually going in this diagonal shape. So this would make it the trans isomer. Now again, same as this, as long as one of them fulfills the requirement, meaning the two methyls here being diagonal fulfills the requirement. So this way diagonal, they do not have to be the same group. It's okay if they're different. Geometrical isomerism is also possible in cyclic compounds because there's limited rotation around the carbon-carbon single bonds in the rings. So for example, here in a cis isomer, there are two wedged lines, as you can see over there, that show the functional groups are coming out of the page. So they're both going in the same direction. And because they are going in the same direction, they are cis. In the trans isomer, there is one wedged line and there is one wedged line and there is one dashed line, showing that this methyl group up here is coming out of the page, whereas the OH group is going into the page. And because they are different directions, this is a trans isomer. So you can see here another example of this. Here they are both wedged lines, meaning that they are both coming out of the page. And since they're both coming out of the page and going the same direction, this would also be cis. Whereas for this one, there is a wedged line and then there is a dashed line showing one functional group to be coming out of the page and one functional group to be going into the page. And since they are in different directions, this is a trans isomer. The second kind of stereoisomerism is optical isomerism, where if a molecule contains a carbon atom bonded to 4 different atoms or groups, it can have 2 optical isomers. And this carbon will be asymmetrical because there will be no plane of symmetry. So for example, if we look at these top 2 molecules up here, we can see that this molecule is actually symmetrical because it's a tetrahedral shape. And any molecule with a tetrahedral shape with 4 of the same atoms or groups bonded to it, in which case all 4 are hydrogens, would be symmetrical. So since here there is a plane of symmetry, this means that this will not have any chiral centers. Also, because the carbon atom is bonded to 4 of the same group, which does not fulfill the requirements of optical isomerism that require a carbon atom being bonded to 4 different groups, meaning, again, it cannot be an optical isomer. Whereas for a molecule like this, you can see that there are 4 different groups bonded here, right? There's a hydrogen, a bromine, an alcohol group, and a methyl group bonded to the main carbon, meaning that this carbon is chiral. And to represent chirality, we use an asterisk, like this. This means that this carbon atom is chiral, and hence this molecule will have 2 optical isomers. And what I mean by optical isomerism is this. So take a look at these 2 molecules. This just represents a mirror. So you can see that this molecule over here can be mirrored to make this molecule. The carbon and the hydrogen and the other molecules are in the exact same place, except they have been flipped over. So instead of the CH3 being on the left, it is on the right on the side, and this bromine, which was on the right, is now on the left over here. But you can see that these are the 2 different molecules. Now you might be thinking, well, maybe it's just moved around and it's switched. Well, actually that is incorrect because these molecules are not imposable. They are non-superimposable, meaning that they cannot be superimposed. So no matter how they are rotated, they will never be the same molecule. And to show you this, I have this. So if I select this molecule and I bring it over the top of this, you'll be able to see that when I put this on top, yes, the hydrogen and the OH line up, but the bromine covers the methyl and on the left, and the methyl covers the bromine on the right, which means that even if I put this molecule on top of this molecule, it is not the same because the bromine and the methyl are in 2 different places. These 2 optical isomers are called enantiomers. and they are mirror images of each other, and they cannot be superimposed. So the carbon atom has 4 different groups attached to it, and this is its chiral center. And only chiral molecules can have optical isomers. So what is chirality? Well, chirality is when the molecule is not the same as its mirror image, and it does not have a plane of symmetry. It must be optically active, and the carbon has to be bonded to 4 different groups, like I showed you in the previous example. So to give you another example of this, if I drew a few molecules, let's look at this molecule. Now here you can see that there are 4 different groups on it. We have a hydrogen, we have a carboxylic acid, we have an alcohol, and we have a methyl. So the chiral center over here is on this carbon. It cannot be on this carbon because it has 3 hydrogens attached to it, meaning that it does not fulfill the requirements of 3 different groups being present. And it cannot be this carbon either, because if you think about a carboxylic acid, it looks like this. And because it has a double bond, it means that it cannot be bonded to 4 atoms at all, which automatically means that it cannot have optical isomerism. Another example would be if I were to, say, replace this OH with an NH2 group. Again, they're all different, meaning that this would again have a chiral center over here. But if I were to replace this with another CH3 group, these 2 groups are now the same. These 2 groups are now the same, meaning that it no longer fulfills the requirement of 4 different groups being bonded to the chiral carbon. So this is not a chiral molecule and hence does not have optical isomers. Now the key rules to remember with any chiral molecule, but specifically cyclic molecules, are these. First of all, we have to ignore any carbon-carbon double bonds. And I'll explain this a bit more, but you also have to ignore any carbon-carbon only with no other groups. And since it's a ring structure, if we're talking about cyclic compounds, then you have to trace around the ring structures to see if it is actually chiral, because the molecule could be symmetrical or it could be asymmetrical. So let me explain these a bit further. When we're talking about the carbon-carbon double bond, if we look at this, for example, although there are different groups bonded to this carbon, with there being a chlorine and a bromine, it is not bonded to 4 different molecules. It is only bonded to 3. It's bonded to the CH2 here, the Cl here, and the Br here, meaning that it cannot be chiral. What I mean by ignore carbon-carbon only with no other groups means if you see something like this, you know you can automatically ignore it because there are going to be hydrogens only around it. And what this means is that, again, 4 different groups are not bonded to it, and hence it is not chiral. This is really important in ring structures, where you might see something like this, and you'll know that there won't be any chiral carbons in this because they're all bonded to, because all the carbons here are bonded to 2 hydrogens, meaning that they will never have 4 different groups bonded to them. So similarly here, if we're looking at this molecule, we know that all the carbons here are just going to be bonded to 2 hydrogens each, so none of them have 4 different groups bonded to them. However, if we look at this molecule, we said to ignore any carbon-carbon double bonds, so we know we won't be discussing those. And any junctions with 2 bonds can be ignored, so we know that here you'd only have 2 hydrogens and 2 hydrogens, so these are definitely not chiral either. However, if you look at this carbon over here, we can see that if we trace it around this way, first of all, it encounters this double bonded group, which is our first key difference. So we'll go this way, first of all. So you can see that on its way, firstly, you have a double bond. And then after that, you have your CH2 and CH2, and then you come over here to the OH. Alternatively, if you went the other way, so you went this way instead, this route is different from the first because the first thing you encounter is a CH2 instead of a CH, which makes this asymmetrical. And because it has 4 different groups bonded onto it, because it would have a hydrogen over here, an OH over here, and we know that it's different when it goes this way, and we know that it's different when it goes that way, this would be a chiral molecule. So just to simplify it, you have to be able to trace around the molecule and make sure that it is in fact different and it is asymmetrical. Now if we look at this molecule, this is a bit different because yes, this molecule has hydrogen bonded onto here, and that means you might think that it's bonded to 4 different groups, but actually if you were to trace around it, you would find that the path is the same. So here you'd encounter a CH2, here you'd encounter a CH, CH, and CH2 if you went this way. If you went the opposite way, so you went from right to left instead of left to right, you'd find that again you encounter the same thing. You see a CH2, a CH, a CH, and then a CH2. So what this means is that it is the same whether you go clockwise or anti-clockwise, meaning that this is not chiral.